Hey, hello and welcome back everyone. So hopefully a little bit of a quicker one today. We'll see how long it actually takes. But we're kind of continuing along this path of trigonometric integrals. But in fact, today's integrals won't look trigonometric at the beginning. We're going to actually end up using the trigonometric functions to help us simplify the integrals so that we can actually compute them. So what are we thinking when we bring up this term trigonometric substitution? We're thinking about integrating quadratic functions to a very specific power of plus or minus 1/2. And so some examples of these quadratic integrals would be something like 1 over the square root 1 minus x squared dx, because of course in the denominator here that's a quadratic term. We've got the square root of quadratic terms. Overall that's to the power negative 1/2, negative because it's in the denominator. Of course we know what the integral of this is. It's sine inverse of x. But today we're going to kind of start to figure out how we could arrive at that answer, maybe without already knowing that the integral is sine inverse of x. So it's integrals of that form. You can imagine something else like root 2 minus 2x plus x squared. Another great example, dx. How would we integrate something like that? So we're going to focus on those today. And it doesn't feel like we should use trigonometric functions right away, but you saw in that example of sine inverse that, yeah, trigonometric functions show up. We're going to have to start out with a topic that you probably approached in Algebra 2, maybe even in geometry. So this is called completing the square. And I'm going to give a really quick example before you look at the expression there. Let's just look at the example. X squared minus 2x plus 2 can be rewritten as x minus 1 squared plus 1. Now, if you don't believe me on that, let's just go ahead and FOIL out x minus 1 squared and see what we get. If we FOIL out x minus 1 squared, it's 2 copies of that. My first terms are going to give me x, my outside term is going to give me minus x, my inside is going to give me minus x, my last terms are going to give me plus 1. So altogether that FOILs out to x squared minus 2x plus 1. But what do you know? I didn't have just the x minus 1 squared. I've also added one extra term to it. So if I go ahead and add one extra term to each of these, we end up with x squared minus 2x plus 2. So that's a procedure of completing the square, really to rewrite a quadratic with 3 terms as a quadratic with only 2 terms, and namely the first term happens to be squared. And this is very useful. For example, let's say we wanted to solve this quadratic, x squared minus 2x plus 2. Let's say we want to know when it's equal to 3, for example. You might not know how to do that, except maybe use a quadratic formula. You'd have to bring 3 to the left-hand side to do that and then use the quadratic formula. What we can do instead is we can complete the square on the left, and we just saw that the completed square version was x minus 1 squared plus 1. Once we've completed the square, it's actually quite straightforward how to finish solving for x. So we're going to subtract 1 from both sides. That's going to give me x minus 1 squared is equal to 2. We're going to take a square root of both sides. It's going to say x minus 1 is plus or minus root 2. And finally, we'll add 1 to both sides. You see that x is 1 plus or minus root 2. It's the same answer we would have got if we decided to use the quadratic formula. But completing the square was kind of an alternative approach to solving quadratic expressions. The question really becomes, how did I move from this first quadratic of x squared minus 2x plus 2 into the second quadratic x minus 1 squared plus 1. That is the procedure of completing the square. Let's talk about how it works. So it works, you're always going to identify your 3 coefficients, just like in any other quadratic, a, b, and c. And the completed square term, recall that it consists of exactly 2 pieces. It consists of kind of x plus something squared and then a leftover constant. The first part, that's x plus something squared, well, you have to factor the a out because you don't want an a on the inside. It would look like the square root of a then, which is a little bit ugly. So you factor the a out front, and then what's left over is really b over 2a. And that's because if I pull an a out here, I would really be factoring an a out of b as well if I wanted to. And then to complete the square, because when I FOIL terms, I have twice the inside terms together, twice b over 2a would just give me the b over a. That would end up if I factored out an a. So that's why this term is going to show up as it does. The remainder term here, c minus b squared over 4a, it's really because I want to end up with c at the end of the day. What would happen if I squared, because there's a square here, the b over 2a, that would give me b squared over 4a squared. But because there's an a out front here, the a out front also multiplies that and it gets rid of that square. You end up with b squared over 4a. You don't want that around, so you subtract it off afterwards. So that's where this formula is coming from. Let's just see it really quick with that first example I wrote, which was x squared minus 2x plus 2. How could I use the example? Well, a ends up being 1, b ends up being negative 2, c ends up being 2. That means I'm going to get 1x plus b over 2a squared plus c minus b squared over 4a. If I go ahead and simplify all these terms, what's it look like? Well, the 1 doesn't matter. I'll have an x minus, what is negative 2 over 2? That's just going to be x minus 1 squared. And c will be 2 minus 4 divided by 4. 4 divided by 4 is 1. 2 minus 1 is 1. And so that's where I ended up with this x minus 1 squared plus 1. If we do the same thing with our other example that I've brought here, something like 2x squared plus 4x plus 3 equals 1, I can go ahead and solve this quadratic by completing the square. Now, how am I going to complete the square? I have to identify a, that's going to be 2, identify b, It's going to be 4. I identify C. It's going to be 3, and I'm just going to plug them all into my completed square equation. That's going to give me, after some simplification, 2x plus 1 squared plus 1. And so the original quadratic, which had 3 terms, can now be written with 2 terms. And if I want to solve that quadratic equal to 1, well, now that it's written in completed the square form, I'm just going to subtract 1 from both sides. It's going to give me 0 on the right. And divide by 2, still a 0 on the right. Take a square root, still a 0. And finally, subtract 1 from both sides. It's going to tell me that x is equal to negative 1. Let's verify that really quick. If I put a negative 1 in here, 2 times negative 1 squared plus 4 times negative 1 plus 3. Let's simplify that. 2 times negative 1 squared is 2. Plus 4 times negative 1, that'll be minus 4. Plus 3. 2 minus 4 is negative 2. Plus 3 is 1. So that definitely worked for us. We can move to the next example, which derives the quadratic formula for us. It's probably been a while since you've seen a derivation of the quadratic formula. You might wonder where it comes from. Let's just use completing the square to solve for what x values will solve this quadratic equation. We're going to complete the square. Well, we just got a, b, and c, so that's literally just me completing the square with a, b, and c in my formula. That's going to be equal to 0 because my original equation was equal to 0. And now we're going to actually use this and solve for x. Well, to solve for x, I've got to subtract, right, because I've got a plus here, so I'll subtract c minus b squared over 4a from both sides, or equivalently, I could add b squared over 4a minus c at both sides. That's what I've got here. And then I'm going to go ahead and divide both sides by a. That's going to give me b squared over 4a squared and a c over a, also known as b squared minus 4ac all over 4a squared. And if I happen to take a square root to both sides, that'll be a plus or minus root b squared minus 4ac over 4a squared. If I want to distribute my square root to both the numerator and the denominator, my denominator is root 4a squared, also known as 2a. We're getting really, really close, right? Because we've got something like plus or minus root b squared minus 4ac over 2a. What's left on the left-hand side, b over 2a, let's subtract b over 2a from both sides. We get negative b over 2a plus or minus root b squared minus 4ac over 2a. And because my denominators are the same, I can get away with combining them. X is negative b plus or minus the square root b squared minus 4ac all over 2a. So this is actually how we derive the quadratic formula. We do always complete the square to get there. Now, what does this have to do with integrating? Well, as I said before, we're going to be integrating kind of square roots of quadratics, and it's going to be quite a bit to our advantage to rewrite the square roots of quadratics as really square roots of completed squares. Well, if I complete the square to the quadratic, my formula is a times x minus b over 2a squared plus c minus b squared over 4a squared. And when we think about it, depending on the sign of a, and depending on the sign here of c minus b squared over 4a squared, both of those could be either positive or negative. We can kind of lump those terms together. I'm going to call a, the a hanging out front, alpha squared. I want it to always be a positive number. I'm going to call c minus b squared over 4a squared gamma squared. And although it doesn't matter quite as much, this negative b over 2a, I'll call negative beta. But what's really important is kind of the a here and the c minus b squared over 4a squared. By completing the square, I should always be able to rewrite a square root of a quadratic in one of 3 cases. So my first case is where the term a out front is positive, and then the leftover c minus b squared over 4a squared is also positive. That's my first case. In my second case, my a out front is positive, but my c minus b squared over 4a squared is negative. And then in my third case, let's say my a was actually negative, and my c minus b squared over 4a squared was positive. So there's going to be 3 cases that could be the outputs of completing the square. We're going to want to pay attention to each of those for today's topic. So let's actually talk about what trigonometric substitution for integrals is. It consists of starting with my root of my quadratic and obtaining one of the 3 forms by completing the square on it. So basically I can assume up to completing the square that I'm in one of these 3 cases. We'll see what it looks like to be in one of those later. So let's assume we have an integral with 1, 2, or 3. Then what do we do? Well, in case 1, we're going to define a substitution. Now, this is just like u substitution, but it looks uglier. This is why we call it trigonometric substitution. We're going to substitute a trigonometric function in for x instead of just u in for x. Okay, so we're in case 1. It's the first case up above. We're going to substitute for x minus beta, and we know that x minus beta is always in my formula. So whatever that x minus beta is, we're going to replace it with gamma over alpha tangent of theta. And if you do this and rewrite it as gamma over alpha tangent of theta, you find out that dx, kind of the very last part of your integral, has to be replaced with gamma over alpha secant squared of theta d theta. If you happen to be in case 2, so that's where we're here, we're instead going to replace x minus beta with gamma over alpha secant theta. And if you make that statement for substitution, you end up finding that dx is gamma over alpha secant theta tangent theta d theta. And if we're in case 3, which is the case where a was negative, we're going to define x minus beta is gamma over alpha sine of theta, and then dx will end up being gamma over alpha cosine theta d theta. Now, where are each of these actually coming from? Because I don't actually write in the book where these come from. Let's go back to the Pythagorean identity, which says that sine squared of theta plus cosine squared of theta equals 1, or if we divide everything by cosine squared, tangent squared of theta plus 1 is secant squared of theta. So we have those two statements. The reason why we're making these specific substitutions is that if I look here, I have something squared plus something else squared. So there are two terms that are squared added together. It'll make it a little clearer if I put squares on both of these ones, because 1 is itself squared. If you look at the tangent case, that's something squared plus something squared. And so we're kind of comparing here. Notice in the first case, I have something squared plus a constant squared. And you'll notice, what did I substitute x minus beta for? In the first case, I substituted for tangent. It's not a surprise because we had a tangent there. In the second case, I have something squared minus another thing squared. Now, there are currently no minuses up here, but let's think about how I could rearrange to maybe obtain a minus. If I took this plus 1 squared and I brought it over to the right, you find out tangent squared is secant squared theta minus 1 squared. And this is where we have something squared minus a constant squared. That was exactly what case 2 was like. And so in case 2, we're going to make the choice to do secant theta, because that's what's on the term, that's squared minus a constant squared. And finally, in the last case, I have something, a constant squared minus something else squared. And if we think about rearranging our sine squared plus cosine squared term, let's bring the sine squared to the right. We have cosine squared theta is 1 squared minus sine squared theta. And so we have a constant squared minus something else squared. That's why we're making the change of variables into sine in the third case. So all three cases reflect the Pythagorean identities, just rearranged a little bit. Now, how does this work? Well, it works in step 3 here, where necessarily, once we make this substitution, the expressions that we started with, which were roots of a lot of things squared, all simplify. And it's because of the Pythagorean identity that these all simplify. In the first case, it'll simplify just to gamma secant theta. In the second case, it simplifies to gamma tangent theta, and in the third to gamma cosine theta. And let's even pay attention a little bit more, because if I look in the first case at d theta, if d theta is coming around, all we're getting is really something like secant to the third power, or these secants are going to interact with each other somehow, which is easier to work with than square roots of quadratics. In the second case, we'll have a gamma tangent against a secant tangent, and somehow those will interact, which will be easier than working with the square root of a quadratic. And in the third case, I'll have a gamma cosine interacting with gamma cosine, so you'll have something like cosine squareds. This is why this section always has to come after us being able to analyze integrals of trigonometric functions, because we will eventually be integrating trigonometric functions here. It's just our first integrals started with quadratics or square roots of quadratics, and then we transform them into integrals of trigonometric functions. So at this step, in part 4, we would be able to simplify the integrands and actually integrate in theta. This will always just jump back to the previous section where we're integrating powers of trigonometric functions. And then when we're finished integrating the variable theta, we can make the reverse substitution, which is just me inverting these, right? Each of these are going to get swapped backwards, solved for theta. In the first case, theta would be inverse tangent alpha over gamma x minus beta. In the second, theta would be inverse secant alpha over gamma x minus beta. And in the third, theta will be inverse sine alpha over gamma x minus beta. So you're going to replace theta with each of these terms, and you'll just end up with kind of a collection that's completely in the variable x. In step 6, something that's optional, I think a lot of professors do require this, you have to use the unit circle as well as a lot of trigonometric identities and the definitions of the trigonometric functions and their inverses to simplify everything in terms of x. Because there is definitely simplification that can always happen when you finish trigonometric substitution. Okay, so this was all a mouthful. I mean, completing the square part of today was fairly straightforward. This is definitely a mouthful. It looks better when you do it in person. It doesn't look that much better, but it does look better. And so let's look at a nice example here, where we're going to integrate 1 over the square root of 9x squared minus 36x plus 37. In step 1, we're always going to have to complete the square of the quadratic. So in this case, we're identifying a, b, and c. And let's recall how we complete the square. It's going to look like a times x minus b over 2a squared plus c minus b squared over 4a squared. And we'll plug these all in. A is 9, x minus negative 36 over 2 times 9 squared plus 37 minus negative 36 squared, all over 4 times 9 squared. You would not want to do this by hand, but supposing you had a calculator or something out, you get 9 times x minus 2 squared plus 1. And now that's important that we recognize the form that everything's been written in after we've completed the square, because the form, at least as far as trig sub cares, we need to have this alpha squared x minus beta squared plus gamma squared form. So we have to identify alpha as actually 3. It's the square root of that 9. Beta can get away with being 2, but gamma needs to be 1 because it's actually the square root of 1, even though that's the same number here. So we have alpha is 3, beta is 2, gamma is 1. And in fact, because this is a plus sign, we are in case 1. Okay, so if we're in case 1 with alpha is 3, beta is 2, and gamma is 1, let's scroll up and see what that's telling us to do. Case 1 says define x minus beta is gamma over alpha tangent of theta. So we're going to do x minus beta, which is x minus 2, is gamma over alpha, 1/3, tangent of theta. And then if you want, following this, just continue as with normal u sub. Okay, you could either follow the steps that we have already given, but if you just want to think about it, we've gone far enough, we've made a choice for substitution. From this point onwards, everything proceeds just like u sub, like regular u substitution. So what does that mean? Well, it means to find dx. How do we find dx? We're going to have to take the differential of both sides here. We're going to get dx on the left because the 2 is a constant. On the right, the 1/3 will come along. What's the derivative of tangent? The derivative of tangent is secant squared, and then we're going to get the d theta coming from the chain rule on tangent of theta. So dx ends up being 1/3 secant squared, which means that our original integral up here, which is also written as, because of completing the square, 1 over 3 squared x minus 2 squared plus 1 squared, dx, we can substitute x minus 2 for 1/3 tangent theta. We can substitute dx for 1/3 secant squared theta d theta. And so if we go ahead and make those substitutions, what do we actually get? Well, we get the integral 1 divided by root, there's a 3 squared, but now the x minus 2 I'm replacing with 1/3 tangent of theta. So I have a 1/3 tangent of theta squared plus 1, and then dx is replaced with 1/3 secant squared theta d theta. I can simplify what's in the denominator. How does this simplify? Well, I have a 3 squared and I have a 1/3 squared, so those are going to perfectly cancel. My denominator is just going to be square root tangent squared theta plus 1. At this point, what you get in your square root will always be a Pythagorean identity. Absolutely, there's no question about it. This will always be a Pythagorean identity. Now I should keep in mind there's the 1/3 secant squared that's still around. So I've got 1/3 secant squared theta d theta that's still here. But at least so far as my denominator is concerned, I have a Pythagorean identity. Tangent squared plus 1 in Pythagorean identity form is just secant squared. And so now I have a square root of secant squared theta, as well as my 1/3 secant squared theta d theta. And if I simplify everything, this is just 1/3. The root of secant squared is going to cancel. I'll have 1 secant squared in the denominator. That's going to exactly cancel with one of my secants in the numerator, and I'm just going to be left with the integral of secant of theta d theta. And so by making my trigonometric substitution, that's the integral I have to compute rather than my original integral. How do we compute 1/3 secant theta? Well, it's bad because we did it at the end of the last video, but it's not bad if you memorize the answer. So if you memorize the answer, you find out secant, right? Secant is log secant plus tangent. I guess I'm missing my 1/3 that came along for the ride there, but the antiderivative of secant is just log secant plus tangent. And so what we end up with here as our answer is 1/3 log secant of theta plus tangent of theta. Now, why do I have something else here that's not theta? Well, it's because at the end of the day, we're still performing a substitution, aren't we? The substitution we chose in this case was that x minus 2 was 1/3 tangent of theta. So now if I solve this for theta, what do I have? I have 3 times x minus 2 is tangent of theta, or in other words, theta is tan inverse 3x minus 2. And now that I know theta is tan inverse 3x minus 2, I'm going to swap that in for this theta and this theta. There's my tan inverse 3x minus 2, tan inverse 3x minus 2. At this point, this is where I always say in step 6 you should simplify. You should definitely simplify even in step 5. You've got a tangent of tangent inverse, so you can rewrite that as 3 times x minus 2. But really, we want to pay attention to this term, secant of tangent inverse of 3x plus 2. How would we simplify something like that? You don't have to, because your calculators can handle it. but it's really kind of ethically the right thing to do, because that's an ugly way to write your answer. It's like being a carpenter and somebody asks you to make a table, and you nail 4 2x4s to a piece of plywood. You hand it to somebody and you're like, there's your table. Technically it's a table, but nobody's going to be impressed with it. So you might as well go ahead and simplify here. So how do we simplify secant of tangent inverse? Well, I'm going to send you back to example 1.2.23, which really showed that cosine of tangent inverse was root 1 over 1 plus x squared. How does cosine relate to secant? Well, secant is 1 over cosine. So we're looking at 1 over cosine of tangent inverse, which will just be the reciprocal of 1 over 1 plus x squared, also known as root 1 plus x squared. So that's going to be secant of tangent inverse. Of course, we don't have x in this case. Rather than x, we have 3 times x minus 2, so that entire x will be replaced with 3 times x minus 2. What that gives us is a 9 times x minus 2 squared inside of our square root. And so I'm going to replace secant of tan inverse 3 times x minus 2 with root 1 plus 9 x minus 2 squared. And so the antiderivative of 1 over root 9x squared minus 36x plus 37 is 1/3 log of root 1 plus 9x minus 2 squared plus 3x minus 2. Hopefully you can appreciate what trig sub is all about now. We'll move on to the next example, which is the integral of 9 plus 6x plus x squared over root 40 minus 6x minus x squared. Big question becomes, which of the quadratics should we complete the square on? Well, the answer really comes down to the bottom, right? Because that's the term that has the square root around it. But it ends up being both is always the best case in trig sub problems. You don't really want to not complete a square in trig sub problems. So every quadratic is best. So in our case, we'll complete the square on the top. And when we complete the square on the top, what are we going to get? We just end up with x plus 3 squared, because it is a perfect square. When we complete the square on the bottom, we have to go through a little bit of extra work, but we end up with negative x plus 3 squared plus 49. Now let's think about our 3 cases. The first one was alpha squared x minus beta plus gamma squared. The second was alpha squared x minus beta squared minus gamma squared. And the third was gamma squared minus alpha squared x minus beta squared. Which of these cases are we in if we simplify to negative x plus 3 squared plus 49? Well, that negative sign is telling you something really strong right away. It's only there in case 3. So once we're in case 3, we have to identify alpha, beta, and gamma. It's going to be the square root of the terms that we see. In particular, this 49 we're going to think about as 7 squared. The one out front is going to be 1 squared. And in fact, with beta, we'll think about beta as negative 3. So that's going to be alpha, beta, and gamma, and we are definitely in case 3. Now, case 3 tells us to make the substitution with sine. So we're going to make a substitution with sine. We're going to do it by doing x minus beta, or x minus negative 3, is gamma over alpha, 7 sine theta. At this point, I do think it's safe, and we should always kind of think about it this way. We're just going to make this choice and proceed like regular u sub. So proceeding like regular u sub, we're going to take a differential of both sides. It's going to give me a dx on the left, and on the right, I'll have a 7 coming along for the ride. The derivative of sine is cosine of theta d theta. So that's going to be dx. And now my original integral, which I should have rewritten with the numerator x plus 3 squared, that's how the numerator completed the square, denominator became 7 squared minus x plus 3 squared dx. I'm going to have to make the substitution that every x plus 3 I see, so there's one there and there's one there, will be replaced with 7 sine theta. And every dx I see, so that's the one there, will be replaced with 7 cosine theta d theta. So what's that going to look like when I make the substitution? Well, I guess I'm getting a 7 sine theta in the numerator, and that gets squared. And then the denominator, I'm also getting a 7 sine theta squared. And then dx is becoming 7 cosine theta d theta. And at this point, I should go ahead and simplify. So what does my numerator look like? Well, it looks like 49 sine squared theta. My denominator ends up being root 49 minus 49 sine squared theta. And then I've got a 7 cosine theta out here, d theta. So my denominator will have a 7 in it, and then a square root 1 minus sine squared theta. My numerator will just be 49 sine squared theta, and then I've got a 7 cosine theta d theta. At this point, the 7s can cancel. There's 1 and 1, they cancel. And as always, I should always have a Pythagorean identity in the square root. wherever the square root, it has to be a Pythagorean identity. In this case, 1 minus sine squared theta is cosine squared theta. And so I'll replace that denominator with cosine squared theta. Where is this going to send me? I'll have a 49 sine squared theta divided by square root cosine squared theta, cosine theta d theta. And because my denominator is the square root of a square, that's going to cancel with that cosine. Everything simplifies down to 49 integral sine squared theta d theta. So now this is the integral I'll actually have to compute. And to compute that integral, there's all my work. Here it is, 49 sine squared theta. To go ahead and compute that integral, we're going to go back to what we learned in the previous video and replace sine with its Euler's identity version, e to the I theta minus e to the minus I theta over 2i. At this point, I'm going to distribute the 2 in the power. When I distribute the 2 in the power, the denominator becomes negative 4 because it's 4i squared. And then the numerator I'll have to FOIL. These are my first terms together, my middle terms together, and then my last terms. And what we'll end up with is the middle terms, as always in these cases, I'm going to add exponents together. They cancel each other. I'm just going to get 2 e to the 0 power. And then the first terms will be e to the 2 theta. The last terms, e to the minus I2 theta. And so if I integrate e to the I2 theta, I pay the price of the coefficient, which is 2i. If I integrate e to the minus I2 theta, I pay the price of the coefficient, which is negative 2i. And integrating 2 d theta just gives me 2 theta. And then I start to ask myself, hey, is what's sitting around here with these exponentials some version of sine or cosine? The answer is definitely yes, sine or cosine. Which one is it? Well, this minus sign is helping me decide that there should be a minus sign. Turns out that this is exactly sine 2 theta. So if I replace those terms with sine 2 theta, then I just get negative 49 fourths sine 2 theta plus 2 theta. Or if I distribute my negative 49 fourths, I have negative 49 fourths sine 2 theta minus 49 halves theta. Making the reverse substitution, right, because my original substitution was x plus 3 is equal to 7 sine theta. Well, I could divide both sides by 7. That tells me x plus 3 over 7 is sine theta. And if I take sine inverse of both sides, sine inverse x plus 3 over 7 is equal to theta. And I'm going to replace every copy of theta here and here with sine inverse x plus 3 over 7. And so that's what you see. We've got negative 49 fourths sine of, because I had a 2 out front here, the 2 needs to survive, but I'm replacing the theta here with sine inverse x plus 3 over 7. Same thing's happening with this theta. It becomes sine inverse x plus 3 over 7. Now, this final case, sine inverse has no simplifications allowed on it, so there's not really much we're going to do there. But going back to the carpenter and his plywood table that we don't want, sine of 2 sine inverse can be simplified, right? It's almost like sine of sine inverse definitely can be simplified. So you would expect sine of 2 sine inverse to be able to be simplified. And it certainly can. We're going to use some double angle formulas for this. So it turns out sine of 2 theta, if you go back to your double angle formula page, sine of 2 theta is 2 sine theta cosine theta, which means I can replace theta with sine inverse x plus 3 over 7 in both of these terms. And what do I end up with? Well, I have 2 sine of sine inverse. Very easy to simplify those. They just cancel the sines, and we get x plus 3 over 7. A little bit trickier on the cosine side. Cosine of sine inverse, how do I compute that? Well, I've drawn it in as root 1 minus x plus 3 over 7 squared. Let's talk about y really quick. Why should cosine of sine inverse be, let's write it like this, cosine of sine inverse of x, why should that be root 1 minus x squared? Well, if we think about a right triangle, sine by itself would be the opposite over the hypotenuse, but when you take sine inverse, its input ends up being the opposite x over the hypotenuse 1. If you take x divided by 1, you get x. And then sine inverse provides the angle associated with that opposite over the hypotenuse. Well, now if we go ahead and ask for cosine of this sine inverse, cosine is going to be the adjacent over the hypotenuse. So this will be the adjacent, whatever that is, divided by 1. So we just need to figure out what the adjacent side length is. The Pythagorean theorem tells you that a squared plus b squared equals c squared, or in other words, a squared, the adjacent, squared, equals c squared minus b squared. Well, if c is 1 and b is x, that says the adjacent squared happens to be 1 squared minus x squared, or if I take a square root of both sides, the adjacent is 1 minus x squared. And so cosine of sine inverse is root 1 minus x squared. So that's how you would simplify the cosine of sine inverse term. And if you bring everything together, so simplify this as this, and then include it in our answer, we find out that the integral of 9 plus 6x plus x squared over 40 minus 6x minus x squared, when I've simplified everything, comes to x plus 3 over 2 times 49 minus x plus 3 squared to the 1/2 minus 49 halves, sine inverse x plus 3 over 7 plus c. Anyway, I do have one more example. You can go ahead and read it in the book. It's even longer than the previous one, so I really don't want to get into it when this video has already been a touch long. So I'm going to skip over that example for now, and what we're going to talk about at the very end of this section is my concluding remarks on integration techniques. Because we were already a little overwhelmed just using substitution and integration by parts. Now we've added, in some ways, 3 new integration techniques between partial fractions decomposition, integrating Trig's functions with Euler's identities, and now trigonometric substitution for square roots of quadratics. We have just so many options when it comes to integrating, and it may feel overwhelming. It is overwhelming. It's a really hard thing to do, but I do provide a little bit of my intuition, at the very least, at the end of this section, to say when we should use all of these. It's not an exhaustive formula. You can go wrong if you follow this. Nothing's perfect when it comes to integrating, which kind of sucks, but it's what you have to put up with as a mathematician. And here's my formula, which is to use U substitution when you can find both a function in parentheses and multiplication by that function's derivative up to perhaps a constant multiple. You're going to want to use integration by parts when you can find 2 functions multiplied together, and the acronym LIATE can be applied. You use partial fraction decomposition when you have rational functions, which are ratios of polynomials. You'll use Euler's identity for products or quotients of purely trigonometric functions. And finally, you'll use trigonometric substitution if you're looking at quadratic functions to a power plus or minus 1/2. That's the best I can do. Otherwise, it's practice, 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 and you get better with time. Anyway, I'll see you in the next one where we're going to apply partial fractions to summations instead of integrations. Bye.